All right, ladies and gentlemen, as promised, and I know you're just so excited for this is the video on going through titration calculations, and this is just in case we're not meeting on Friday, or in case you need to go back and look at how it is that we're doing these problems, in case you want to have a second look at them. So just a reminder where we are. We already talked about how we determine the initial pH in a titration, because we're constantly asking what is in the flask. And when we have an initial pH, then the only thing that's in the flask is usually the acid, but it also could be the base, but you haven't started combining the two. So the pH is simply based on the concentration of whatever it is that you're starting with. And now we're going to be talking about how you determine the pH between that initial starting time and before you hit your equivalence point, which is what I say from beginning to the middle. The equivalence point is sort of the middle of your titration, when moles of acid are equal to moles of base, and we're talking about somewhere in between there. I will be referring to the practice problems. These are the practice problems that are on the very last page from the practice problem set. You'll want to have a calculator out. You'll want to have these problems out so that you can make notes and follow along. When we are not at the initial starting point of our titration, and we are not at the equivalence point, by asking ourselves what is in the flask, what we really mean is, what is it that's in the flask that's controlling pH, that would have an influence on pH? And how much of that stuff is there? How much of it has been used up versus how much of it is still there, either because you added it from the burette or because you started with it in the first place. So recalling, because we set this up in both classes, but just to remember where we left off, it's crucial to think about the reaction that's occurring. This is an acid-base reaction, and as we had already, we had our sodium hydroxide reacting with the hydrochloric acid, and we're creating water and sodium chloride. And then we're thinking about, because this is, all these things are going to be in the flask in our titration. Sodium hydroxide has an effect on pH. It's a base. Of course it does. Hydrochloric acid has an effect on pH. It's an acid. Of course it does. Water is neutral. Water is not going to come into play in terms of impacting the pH. Neither is sodium chloride. Not because it's a salt. We need to break that habit of simply saying, well, it's ionic, so it can't affect pH. Yes, it can. We've been talking about acidic salts and basic salts. But because sodium chloride is a neutral salt, because it comes from the conjugate acid and the conjugate base of a strong base and a strong acid. So it has no impact on pH. We wrote the reaction, and then we figured out moles. So I'm not going to go through the math for figuring out the moles of each one, because by now you should feel comfortable doing that. I gave you volume, I gave you molarity of both the sodium hydroxide and the hydrochloric acid. Therefore, you can determine moles of each, and that's what we left off with, I think, in pretty much both of the classes. We had figured out that there were 0.0048 moles of the NaOH and 0.005 moles of the HCl. And then I introduced this idea of a BCA chart. And in a BCA chart, the initials stand for before, change, and after. In the unit that goes into a BCA chart, and this is key, is the mole. So we're thinking about how many moles of sodium hydroxide we're starting with, how many moles of hydrochloric acid we're starting with. Now, the only things that we're going to fill out for a BCA chart are things that affect pH. We're not going to fill out water. We're not going to fill out sodium chloride. They don't impact pH. Sodium hydroxide and hydrochloric acid absolutely do, though. We look at these numbers. We think, all right, well, which one do we have more of? Which one do we have less of? We have less of the sodium hydroxide. That makes the sodium hydroxide, because they're in a 1-to-1 ratio, the limiting reactant, meaning it is going to get completely used up. We are not going to have any of it left over. 0 moles once the reaction is done. Well, how do you get from 0.0048 to 0? The change has to be minus subtracting all of it. And that's really sort of the key strategy towards looking at your BCA chart. You want to take your smaller number, make your smaller number go to 0. the smaller number, if everything's 1 to 1, is the thing that is the limiting reactant is going to get used up. Because sodium hydroxide and hydrochloric acid react in a 1 to 1 ratio, if I'm using 0.0048 moles of the NaOH, I will also be using 0.0048 moles of the HCl. When I do the subtraction based on how much hydrochloric acid I started with, this is going to mean that I have 0.0002 moles of HCl remaining. So the question of what's in the flask at this point in the titration? Well, once the sodium hydroxide reacts, it's all gone. I don't have any of it. It has all reacted. It has reacted with most of my acid, but there's still 0.0002 moles of the acid that remains. Yeah, I've generated some water. Yeah, I've generated some NaCl, but it doesn't affect the pH, so I'm not going to be concerned with how much I have created. The big thing that we're looking at is this right here. What is in our flask? That is in our flask. 2 times 10 to the minus 4th moles of hydrochloric acid. That's what's in our flask. That's what's controlling pH. With that in mind, we can now start moving towards our pH calculations. We need pH. That's what the question is asking for. And pH, by definition, is the negative log of the hydrogen ion concentration. Well, hydrochloric acid is a strong acid. So whatever the concentration of the hydrochloric acid is, because it completely dissociates, will also be the concentration of the H+, which means that we need the concentration of the H+, which means that we need the concentration of the H+, not the moles. This is not concentration. You cannot take this 0.0002 moles, take the negative log of it, and think you have pH, because you do not. You do not have the molarity. You need the molarity. Molarity is moles per liter, moles of solute per liter of solution. We almost have molarity, but we don't quite have it. So you have to do, there's an additional step. You're not done. You're not just taking the negative log with the 0.0002. We do want that number, though. That's how many moles we have. We've got 0.0002 moles of H+. Then we have to think about volume. What volume do we have? If you think the volume is 50 milliliters, you're wrong. If you think the volume is 48 milliliters, you're wrong. What is in our flask? You have to constantly think that with titration problems. What is in the flask? In this case, we've established that that's the number of moles of H+ we have, but then physically, what is the volume in the flask? You have added 48 milliliters into 50 milliliters. Congratulations, your volume total is 98 milliliters. Additive volumes. Additive volumes. Super important in titration questions. Absolutely crucial in titration questions. When we're finding concentration, we're going to do the moles divided by 0.098 liters. Just doing the conversion right there. That's how we're getting our concentration of our H+. So doing this math, we get 2.04 times 10 to the minus 3rd molar. That is our concentration of our hydrogen ion, and that's the value that we're going to take the negative log of in order to determine the pH. Hopefully you're following along. Hopefully you're pausing this when you need to so that you can do this math, confirm that you get these numbers, and seeing that the pH at this point in our titration is 2.69. Notice that even though we have reacted most of our acid away, we started with 0.005 moles, we used up all but 0.0002, it only caused the pH to go up from 1 to 2.69. That's an increase in hydroxide and a decrease in H+ for sure, but we haven't even yet gotten close to neutral. So that's that question. Next question. How do you determine pH at the equivalence point? What is the pH when 50 milliliters of 0.1 molar NaOH is added to 50 milliliters of 0.1 molar hydrochloric acid? Considering these are categorized, I want to just sort of talk about this a little bit. You have to first of all confirm that we are in fact at the equivalence point. Remember, equivalence point, your moles acid are equal to your moles base. Hopefully, simply by looking at these numbers, you can tell that we have the same volume and same molarity of both the acid and the base. So if you're plugging those numbers into the molarity quote-unquote formula, you know you're going to get the same value. We have 0.005 moles of both of acid and base. 0.005 moles of HCl, 0.005 moles of NaOH. We are at the equivalence point. Now I'm going to write this out in a BCA chart. It's not necessary, but I just sort of want to show you what's happening at this point in the titration. So we've got our sodium hydroxide. Notice I'm rewriting the reaction. That's kind of important for BCA charts. And we're creating water and sodium chloride. I'm going to use the abbreviation BCA. Now, we plug in moles into a BCA chart. So at this point in our titration, we have 0.005 moles of NaOH and 0.005 moles of HCl. We don't care about the water because it's neutral. We don't care about the sodium chloride because it's a neutral salt. We're only looking at things that could affect pH. Sodium hydroxide could affect pH, hydrochloric acid could affect pH. But then if you look at the reactants, the 0.005 moles of NaOH, the 0.005 moles of HCl, you want to take the smaller number and make it go to 0. The smaller number. The smaller number. They're both the same. The change is going to be the same. They are in equivalent amounts, meaning they are going to totally react, meaning you're going to wind up with 0 moles of both of them. They are in the perfect amount with one another to get completely and totally used up. This is our equivalence point. No more acid, no more base. They're both gone because they have totally reacted with one another to create neutral things. Because of this, we know that our H plus must be equal to our hydroxide concentration. It has to be, because there isn't one thing more than the other. They're both the same. The NaOH used up the HCl. This created water, which in pure water, H plus is equal to OH minus. What's the pH? Neutral. 7.00. Getting us in the habit of writing our pHs to 2 decimal places, please. So that's that part of the question, and that's sort of why that's happening. But then the last aspect of our titration calculations, determining the pH after the equivalence point. Similar in tone, what is the pH when 52 milliliters of 0.1 molar sodium hydroxide have been titrated into 50 milliliters of 0.1 molar HCl? We want to start the same way. Notice we've started by doing essentially 2 things. Number 1, writing a reaction. Number 2, finding moles. It's the same reaction, but it's going to help us organize our thoughts. So we're still doing sodium hydroxide plus HCl. By the way, if you wanted to use a net ionic here, that would be totally fine. Goes to H2O plus NaCl. And again, we're thinking about things here that can affect pH. Sodium hydroxide can, hydrochloric acid can. Water cannot, sodium chloride cannot. And again, we're going to do a BCA chart in which we plug in moles. We're getting moles from our volume and our molarity information for each compound. The hydrochloric acid has not changed in moles because that's what we started with in the flask. So that's still the 0.005 moles of HCl. But we have changed the amount of sodium hydroxide because we've added a little bit additional, we've added 2 additional milliliters of sodium hydroxide into the flask. So now, instead of 0.005 moles, we've got 0.0052 moles. We are not interested in the water. We are not interested in the sodium chloride. No effect on pH. It's not going to be a part of our calculations. And once again, we have a BCA chart. We are not at the equivalence point because I do not have the same number of moles of each one. We are, in fact, after it. With the BCA chart, identify your limiting reactant. Identify which one you have less of, if everything is 1-to-1, and make that one go to 0. It's going to be completely used up. Now, if you look at these numbers, you see that the one that we have less of is actually the hydrochloric acid. We have less of it. So it will be completely consumed. How do you get from 0.005 to 0? You have to subtract 0.005 moles. And because the sodium hydroxide and the hydrochloric acid exist or react in a 1-to-1 ratio, if you use up 0.005 moles of hydrochloric acid, then you are also going to use up 0.005 moles of the NaOH. Meaning, what is in the flask at this point in time? 0.0002 moles of sodium hydroxide. What is in our flask? This is what's in our flask. 0.0002 moles of NaOH. We're looking for pH. pH, by definition, is the negative log of the hydrogen ion concentration. If you take the negative log of that number, 0.0002 moles, you are not finding what you think you're finding. Because we need molarity. We have to have molarity in order to do pH calculations. And we don't have that right now. We have moles, which is great, and it's a right step on the way to getting molarity, but it's not our answer. So we've got to calculate molarity. So how many moles do we have? Well, we've got 0.0002 moles. Additive volumes. What is in our flask? What is in our flask? At this point, we have put in 52 milliliters of sodium hydroxide, and we started with 50 milliliters of HCl, which means that we have a total of 102 milliliters in the flask. Doing that math, dividing out the number of moles by the volume, we see that we get a concentration of 1.96 times 10 to the minus third molar. And here's where you have to be careful, because what have we found the concentration of? Don't just blindly go on with your calculations without thinking. What have we found the concentration of? This is moles of NaOH. This is moles of NaOH. This is moles of hydroxide. I know it's moles of hydroxide because I know that NaOH dissociates in a 1-to-1 ratio with the hydroxide ion, which means that I just found the hydroxide ion concentration, not H+, which is fine because you will hopefully feel very comfortable saying, I know how to get to pH from here. We've got two different ways. The way that I'm going to use, which is the way that nearly everyone was choosing to tell me they were doing on the homework, which is perfectly acceptable, I'm going to take the negative log of this number, I'm going to find POH, and go from POH to pH. So take the negative log of that, know that you're finding POH when you do this, and we get a POH value of 2.71, that's a decimal. And then in order to determine pH, we're going to do 14 minus 2.71 to get a pH of 11.29. Which makes sense. We expect this to be basic. We expect this to be above 7 because we have more hydroxide than we do acid. That's what's in the flask. More NaOH than HCl. We used up all the HCl is gone, and then we added a little extra sodium hydroxide, which means that we are ending with a basic pH.